So folks, in the last video, we learned what a multivariable function was, and now we're going to learn how to take partial derivatives of those multivariable functions. So to compare and contrast slightly, we take ordinary derivatives of functions of one variable, and we can take, and there's many types of derivatives, but we can take partial derivatives of multivariable functions. And let's just look at the notation real briefly. If I give you the f of x, let's say it like this, let's say y is equal to f of x, then when I go to talk about the derivative of this function, I might write dy dx. And here I'm using the d symbol, which denotes the ordinary derivative of a real valued function. Notice that this function right here has a single input value and a single output value. And so when we denote the ordinary derivative, we use the letter d. But let's say I gave you a multivariable function, like maybe, for instance, y is a function of f of x and t. So if I were to take the partial derivative of this function, I might denote it as partial y, partial x, or if I were to do it for the other variable, the other independent variable, I might write partial y, partial t. And so here what I want to point out is that this was a multivariable function. We had two input variables. And so when I want to go denote the derivative, I use this partial symbol. Now this partial symbol, notice that this is the letter D, this is the Roman letter D. This is the lowercase Greek letter delta. So we're using kind of the same letter, just a different form of that letter. So real quick, I just want to remind ourselves from first semester calculus, how did we compute the ordinary derivative? So if we had y was equal to f of x, then we said that dy dx was equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, provided this limit exists. So I want to remind you of that derivative that we did in Calc 1, because now we can look at the partial derivatives. So here are our definitions for the partial derivatives, and I'm not shortcutting anything here. What I am shortcutting is the interpretation. I'm not really going to go into what does this mean to take a partial derivative, but let's go ahead and give the limit definition of the partial derivative. So if we've got this multivariable function here, f, in this case we would say that f is a function of both x and y. We've got these two independent variables, x and y here. Then if we wanted to talk about the partial derivative of f, with respect to, let's pick the first variable, x, we're going to denote it partial f, partial x. And its definition is, so let's say it like this, partial f, partial x is equal to the limit as h approaches 0 of f of x plus h comma y minus f of x comma y all over h. And so I'd like you to compare and contrast this with the single variable, this is for a single variable, the single variable limit definition of the derivative, where when we took the derivative with respect to x, we allowed the x here to vary by we usually think of that as a small quantity h, and then we subtracted off the original f of x. So we're looking at the change in y all over the change in the x coordinate. So here we're doing the exact same thing. We're going to allow x to vary slightly and ask, how does the output values of the function change as x varies slightly? But notice that this has two independent variables, both x and y, and in this case, the y is not allowed to vary. So I think that you could probably give the next definition on your own, but let's do it together. If we were to take the partial derivative of f with respect to y, first of all, we'll denote it partial f, partial y, and it is, well, partial f, partial y is equal to the limit as h approaches 0 of f of x comma y plus h minus f of x y all over h, where in this case the x coordinate does not change, and I ask the question, how do the output values of f change as y is allowed to change by just a little bit? So it is worth taking just a moment to compare and contrast these two partial derivative definitions with the original ordinary definition of the derivative that we learned in single variable calculus. So let's continue with this. The gist, so this is really what I need you to take from today's lesson. The gist of these definitions means that under most circumstances, when we're taking the partial derivative of f with respect to x, we treat the independent variable as if it were a constant. And we take the ordinary derivative of f with respect to x. So let's put that on pause for just a minute. Let's look at this function right here. This was the one that we studied earlier. It's a multivariable function. There are two independent variables. But I'm asking the question, how does the output value z change as x is allowed to change? So what I'm going to do is I'm going to take the partial derivative of this function z with respect to x, and what do I end up with? Well, what I said up here, the gist, the informal gist of this, is we're going to treat the variable y as if it were a constant, and we're going to ask the question, as x varies, how does f vary? So that's just the ordinary Calc 1 derivative. So what's the derivative of x cubed? It's 3x squared. Now I'm going to put plus 0 for that middle term there, because as far as the variable x is concerned, as x changes a little bit, the expression minus y does not change. Now, it gets a little bit harder when we have interactions between the variables. So in Calc 1, how did we take the derivative of the square root of an expression? Well, it is 1 over 2 times the square root of that expression. But in this case, I have to do a chain rule here. So I'm going to say, how does that inner expression vary as x varies? And so its derivative, again, as if I were treating y as if it were a constant, with respect to x, would be y. So we could clean that up a little bit as 3x squared plus y all over 2 square root of yx. That's where we're taking the partial derivative of this with respect to y. Or excuse me, with respect to x. Careful, folks, I made a mistake there. So let's go ahead and do the next problem. When taking the partial derivative of f with respect to y, we treat the independent variable x as if it also were a constant, and then take the ordinary derivative of f with respect to y. So let's go ahead and take the partial derivative of this function z with respect to y. So partial z, partial y is equal to, so I'm going to get 0 for the first expression, because as y varies, how does that expression change? It doesn't. But as y vary, how does this expression change? Well, we know from Calc 1 that its derivative, its rate of change, as y varies, is minus 1. Plus, and now we're going to take the derivative of this with respect to y. So in Calc 1, we learned that the derivative of the square root of an expression is 1 over 2 times the square root of that expression. But we have a chain rule here. And so I'm going to push us a little bit on the notation here. What we have left is we're going to take the partial derivative of what was inside of there, which was the expression y. Oops, folks, I have an error there. That should be an x. We're going to take the partial derivative of what was inside there, which was the expression yx. We're going to take that partial derivative with respect to y. So I didn't show this step over here, and you don't have to worry about showing this step, but it may actually clarify things for you, how we're doing the chain rule with these multivariable functions. So again, let's say that one more time. How do we take the derivative of the square root of an expression with respect to y? It's 1 over 2 times the square root of that expression, but then we've got to do the chain rule. So we multiply that by the derivative with respect to y of what that inside expression was right there. And so if we finish this out, we'll have minus 1 plus 1 over 2 square root of yx. And then if I ask what is the partial derivative of this expression with respect to y, I'm going to take the derivative of this expression, treating x as if it were a constant. And what's the derivative of just y times x? It would just be the constant x. And so this cleans up to be x over 2 square root of xy minus 1. Folks, I hope this clarified, but we're going to get some more practice on subsequent pages. Thanks for your patience, and I'll see you in the next video.